Chapter 9 of Circuit Analysis 1, EE211, and we will be talking about sinusoids and phasors in this chapter. I do like the sayings at the beginning of each one of these chapters, so there's a nice one of my favorite Persian proverbs is at the bottom here of this slide. It is full of wisdom, and you should all read it. I won't read it to you. You can read it, but read it in your textbook. I also like the beginning of this chapter where it gives you a little bit of career advice. In particular, they're talking about, and they have an ABET criteria cited here. So ABET is an organization that oversees engineering schools and makes sure engineering schools are up to standards and have some uniformity across the U.S. university system. So that's what ABET does. It's an accreditation institution for engineering schools. But they have learning objectives just like your courses have learning objectives. But one of the learning objectives for an engineering school is that an engineer has an ability to function on a multidisciplinary team. And I cannot overemphasize that. As an engineer or a math-inclined person, a lot of times through my schooling, I liked working alone and not in groups of people. And maybe some of you will relate to that as well. And then I always didn't like when people made me work on teams. But when you do get to the workplace, everything is a team. And you may not like everybody on your team, but you want your team to be successful. So learning to get along with everybody and be a team is an important thing. And actually, as I entered my career and worked on teams, I found that by the time somebody had graduated and became an engineer or a scientist of some kind, or a finance person, or a program manager, remember this is interdisciplinary, or they were a mechanical engineer and I was an electrical engineer. They had made it all the way through college and they were talented people that I was working with. And so I did very much enjoy the team aspect of the job, and you also additionally get your time to work on your designs and be your introverted self if you are so inclined, as actually I was. But the team aspect and functioning on a team, especially a multidisciplinary team, is very valuable, and you have to recognize that not everybody is an engineer. So my 2 cents worth in there. The advice at the beginning of this chapter is good. Also, I rarely mention it, but there are nice little historical notes throughout your textbook. I do hope that you are reading them. Since we are entering now the AC world in our material, in our studies, we are now entering the AC world versus the DC world that we've been in all this time. It is relevant to mention Nikola Tesla and George Westinghouse, but in particular Nikola Tesla, and they show Westinghouse's picture. But okay, there's a very interesting story between Nikola Tesla and George Westinghouse. Tesla was absolutely a genius, and besides reading their short little historical blip in the textbook, you should really go to YouTube. There are several very good YouTubes that you can watch about Nikola Tesla's life. Very interesting person, lots of fascinating experiments and work that he did. I would love to repeat them, and that's a conversation for outside this lecture. So anyway, moving on. So I'm going to sort of recap what we've done so far to put it in perspective before we really dive into this chapter. We spent a good portion, at least half the semester, on DC analysis, where we had a DC voltage and a DC current, and DC sources, either voltage or current sources. They did not vary with time, and so that was us learning our Ohm's law, etc. So the circuits did not vary with time. And then in the last chapter, chapter 8, we entered somewhat of a time-varying analysis, and it's appropriate to write our voltages and currents as a function of time starting in this chapter, although your author did do it in the DC world too, but now it's very appropriate to explicitly write that these are functions of time. In chapter 8 we looked at what's called the natural response, which was no sources were in the circuit, but the circuits had like capacitors and inductors in it, or something that could store some kind of a charge that would naturally discharge, and the rate at which it discharged in the circuit was dependent on the circuit values. And then we looked at the step response. So this is a sudden turning on or turning off of a current or voltage source. and we found out what the circuit did. And initially it had some kind of a transient response, which was tied to the circuit's natural response. And then it had a steady state response at time equals infinity. The steady state response was really the DC behavior of that circuit, but DC behavior considering that there were capacitors and inductors in there. So this next chapter, chapter 9 that we're entering now, is a time-varying analysis. So with sinusoidal excitation, we are looking at a steady-state response, but instead of having a DC supply and looking at the steady state, we are going to give an AC signal to our circuits, but in particular we're going to give it a sinusoidal excitation. So we are not, though, looking at the transient response with a sinusoidal excitation. But so anyway, we're looking at a steady state with a sinusoidal excitation. So since it is a sinusoidal excitation, we will have a voltage or a current that varies as a function of time. So again, it's appropriate to have V of t and I of t. So this type signals, this is a voltage signal. This is a sinusoidal voltage signal definition. And so voltage as a function of time is Vm sine omega t. So let's define these terms. These are the ones that we will use throughout circuits, and you will also use them in electromagnetics when you get to that class. So Vm, the M I assume means max here, so it's the peak value of the sinusoid, also called the amplitude of the sinusoid, and I think the M here means max. Omega, the next symbol is omega, it's a Greek letter omega, is the angular frequency, and those units are in radians per second. And then if you multiply omega times t, and t is time, then that's actually the argument of the sinusoid. So in a way it's a little bit sloppy, but they write sine omega t, but remember omega t is actually the argument of the sine function right here. And so it's omega, angular frequency, times time. So radians per second times seconds equals what? Radians. So this argument right here, this argument in here is in radians as it's written, which is, you could have sine something in degrees, but we're having sine something in radians. So recall that 2 pi radians equals 360 degrees. Just refresh people's memories just in case you need to. So this is where we call 0 degrees on our, say, XY axis. And if we draw a unit circle, that's 360 degrees going around. This is 9, and we always go around counterclockwise if we're talking about the degrees. That's 90 degrees, or pi over 2 radians. That's 180 degrees, or pi radians, going around counterclockwise. That's 3 pi over 2 radians, which is 270 degrees. And then we're back here at 360 degrees, or 0 degrees, or 0 radians. So recalling those definitions, which I'm sure you guys have all seen before this class. So we can plot our sinusoidal function, and so it's time on the horizontal axis and voltage on the vertical axis. And we've done a few things. Here's time on the horizontal axis, and you will see that it takes a certain amount of time to complete one full cycle. So this is one full cycle is completed. Here's a second full cycle is completed. And the time that it takes to complete one full cycle is given the name period. That's called the period, and we use the symbol for it as a, oops. The universal symbol for period is t. So t is the period of the waveform, period of the waveform, and it is defined as the time it takes to complete one whole cycle. So it is in seconds. So maybe it takes 2 seconds for the voltage to go up and then back down and complete. So if it takes 2 seconds for a whole cycle to complete, then that period would be 2 seconds. In 1 second, only half of the cycle is completed. So anyway, and then if I make my horizontal axis just for the fun of it omega times t. So now that we're in pure radians, you see it's 2 pi radians to complete a whole cycle, sinusoidal cycle. And from that we can get this definition right here. So definition of a sinusoidal function is a periodic function. So the definition of a periodic function is one that satisfies that the value of the function is the same as the value of the function plus some time interval. So which is shown as an integer times the period right here. So a sinusoid satisfies the definition of a periodic function. Not just a sinusoid does, but square waves do, triangle waves do, as long as it has a constant period, then and that the amplitude remains the same when you sample it at the same point in time within the cycle for n cycles, then it becomes a periodic function. And this is just a math proof saying I have a voltage at some arbitrary time t and I add the period to it, and I just do the algebra through here, and you find out that the by definitions of the period that the voltage at time t plus a period is the same as the voltage at time t. So that makes it a periodic function. So 1 over the period is defined as the frequency, and frequency is going to be in cycles per second or in hertz. And if you are writing something is 5 hertz, you write, this is the units that you would give behind it, like ohms. The units here are hertz. So if you think about a sinusoid, if it is oscillating 1, 2, let's see, 1, 2, 3, 4, 5. This is time. Let's say I have something that oscillates 5 times in 1 second. So it's 5 cycles in 1 second. And so its frequency would be 5 hertz. So if I think about that, how long did it take it to complete 1 cycle? It took 1/5 of that. So the period here is 1/5 of it, or 0.2 seconds. So you can actually think about the fact that they are inverses and not just take the formula for granted. So for example, 5 cycles in 1 second means it would take 1/5 of a second to complete 1 cycle. So 1/5 of the second is the time it takes to complete 1 cycle, which is the period. So frequency is really important, not just as a concept thing, but they occur all over. From frequency of 0 is DC values. The voice that we use to speak in averages around 3 kilohertz of frequency. Our audio range that we can hear is between about 60 hertz to, if you are a young person under 25 years old, you probably hear up to about 21 kilohertz. As you get older, you hear less and less. I, for example, hear only up to about 17 kilohertz right now, but I'm doing ahead of most people my age who are only hearing to around 14 kilohertz right now, and that has to do with a stiffening of cartilage and things in your ears. So audio ranges are down here in the kilohertz. So 1 kilohertz is 1 times 10 to the 3 right here. 3 kilohertz is in here. So our audio ranges are in this area. After that, we can get to AM frequencies, like your AM radio. When you listen to an AM radio, it has a number associated it, and it will be at such and such megahertz, right? So AM frequencies are in the megahertz. 10 to the 6 is megahertz. FM channels, think of our radio station. For example, we have 103 point something megahertz is a channel Shaka I listen to here. It's classic rock. So 103 megahertz is 10 to the 8th hertz. And then we go up to microwave frequencies. Your cell phones are transmitting at microwave frequencies in this area. So and then after that we get into the infrared spectra. So infrared spectra, think of that, you see 10 to the 12th. So that's gigahertz frequencies. Visible light is in the terahertz, 10 to the 15th frequencies. So these are all frequencies. Usually when we get up to these very fast frequencies, these are oscillating many, many times a second. So this is 10 to the 14th times per second. This frequency will oscillate. And we usually stop talking about it in hertz anymore, and we start talking about it in wavelengths. But that's a different lesson. So there's a relationship between wavelength and frequency as well. So okay, so a little bit background on frequency. We've now defined frequency. So more general expression for our sinusoidal, this is a voltage sinusoid that we've been talking about, is that it will have the max value. So see, max value is right here, times sine omega t plus a phase. So phase is telling you where it's starting compared to some zero reference time. At t equals 0, sine omega t starts here, and the voltage varies as a function of time, plotting here. But if I add a phase here, so I said plus a phase right here, and then I look at the second signal right here, I'm saying basically, and you can plot it to see, that the second function, V2, leads V1 by an amount, a phase amount, phi. That's a Greek letter phi, P-H-I, phi. So it leads it because it starts from its zero crossing point before this one does. So we say it leads. We could similarly say that V1 lags V2 by this amount, this angular amount phi. So either V2 leads V1 or V1 lags V2. And this angular amount is this phase amount phi. But the way you say is by looking at where the sinusoid starts, where it crosses 0 and starts. Not where it crosses 0 right here, but it starts, it crosses 0 here, and goes positive. This one starts here. It starts sooner in time. Time is sooner here. So this function leads this function. And that's going to become important as we talk about phasors. So we can use our trig identities to express sines as cosines or cosines as sines or vice versa, and to add two different angles. There's lots of like sine of angle A plus angle B, and you can apply this trig function, cosine of angle A plus angle B, and you can apply this other trig function. And if you use these two functions and you put in 180 degrees or 90 degrees, you get forms that look like this. So I sometimes don't remember the formulas, but I can usually think it out. So I'm going to go ahead and show you my thought processes thinking them out. So remember that we're always going around a positive angle is going around counterclockwise, and we start at 0 degrees here. So if I just arbitrarily, I picked some angle right here, it probably is about 60 degrees. So if I say sine of some omega t that maybe is right here, 60 degrees, plus 180 degrees, plus 180 degrees is opposing. So plus 180 degrees, I go 180 degrees over here. That's now this angle right here. And so sine of this amount is right here, and if it was 60 degrees, that would be 0.866. So sine of 60 plus 180 degrees equals, so 60 plus 180 would be 240, it's right here, or it would be 180 plus 60 that way. So the sine of that is a negative amount, is minus 0.866, or square root of 3 over 2. And that's the exact same thing as saying sine of minus the sine of 60 degrees here, sorry. Minus the sine. The sine here is that, and minus of it would be make it a negative sign, so it would be a 0.866. So I can sort of, I sometimes forget the formulas, but if you think of the circle that you use to define all of these angles, get rid of that, you can walk through what's happening. So another one that I did down here is, well, sine of something plus 90 degrees. So I think of where I am in the quadrant. So let's say I'm right here in this quadrant, and I go 90 degrees. I'm over here in the second quadrant of my unit circle, and the sine of this amount is right here, and that's going to be equivalent to the cosine of this angle that's over here. So the cosine, this length is going to be the same as this length. So I oftentimes think of it in terms of the quadrants. Yes. So there's also a graphical technique. Well, there's two things that you can do if you want to add A cosine something plus B sine something. There's a couple of ways you can a couple of different ways you can approach this problem. One way is to take the cosine and convert it to a sine. And then you can add two sines together, which is fine. So I can convert my cosine to a sine using some of these formulas. Or I can convert my sine to a cosine, and then I can add two things together that are both cosine. Or I can use this formula here and get the result from a calculation, which is actually related to the fact that I'm dealing with right triangles. And so the amplitude of the resultant through the Pythagorean theorem, C will be this, through the fact of Pythagorean theorem and a right triangle, you can get the resultant amplitude here, and you can get the angle that it's at relative to the starting angle, which is along here where omega t is. You can get it from this formula. So here I have an example. 3 cosine omega t would be a vector of length 3. It's a vector of length 3 plotted this direction in the cosine omega t direction. And then using this graphical method, the sine omega t points downward, but it's minus 4 sine, so I'm going to be pointing upwards, and I get a vector in this other direction with this negative amplitude here. And then by the Pythagorean theorem, I can find the amplitude of the resultant right here, and you can see it graphically, and then you can see this angle between them from the formula. So there is also additionally a graphical approach. So let's do an example from your textbook. So find the amplitude, phase, period, and frequency of this sinusoid. So some things you can get just by inspection. The amplitude is the max, it's V peak. So it's going to be 12 volts. The phase, just looking at it, is 10 degrees. I can just look at it. The angular frequency right here is 50, just by looking at it, because the form is omega t plus a phase right here. The period, you have to apply a formula. So 2 pi over the angular frequency, and you get a period in seconds. And then the frequency is 1 over the period, but the frequency is also can be gotten from omega equals 2 pi f is the other way you get it. So the frequency can also be gotten by this formula. So not too bad so far. So here is another problem that we should look at. Calculate the phase angle between V1, which is a cosinusoidal function. By the way, these are, whether you say cosine or sine, it's still considered a sinusoidal function. And V2 is this sinusoidal function, and state which sinusoid is leading. So method 1 is to just do it with our trigonometry identities. So we have to express either both of them as cosine functions so that you can add them up, because omega t doesn't change, that only the phases change. Or you can express them both as sinusoidal functions, and you need to get them both with positive amplitude. So method 2, they convert everything to a sinusoidal function. Method 1 is convert everything to a cosinusoidal function. So the first thing is you also have to worry about our amplitudes being both positive if you're doing this technique. So here was V1. You apply some, so it's minus 10 in the amplitude, which means we can say minus 180 and make the amplitude plus. And then you'll get what V1 is right here. So V2, we need to convert this sinusoid into cosine, so we apply a trig identity to it and we get the cosine. So they both have positive amplitudes, and we can see one's at minus 130 degrees relative to the 0 starting point, and one's at minus 100. So the difference there is 30 degrees. So method 2, I'm not going to go over. It's another trig identity, but only converting them both to sinusoids instead of cosinusoids. So method 3 is their graphical approach, using this cosine on the horizontal axis and sine on the downward pointing vertical axis. So I have a little bit of a, I'll go how I think through it. So V1 is minus 10 cosine something plus 50. So plus 50 always means to go plus is clockwise. So I go plus 50 degrees right here because 50 is clockwise. Plus 50 is clockwise. And I say the amplitude is 10. Oops, no, it's not 10. It's minus 10. So I just go to the negative, the opposite direction, and that's at minus 10. So here is my first signal, V1. Another way you can look at it is plus would be this way, minus is this way, so minus 10 is this way, plus 10 is this way, and then plus 50, 50 is always clockwise. So 50 is always clockwise. I went plus 50 clockwise that way. So plus 10 is this way, minus 10 is this way, plus 50 degrees points it that way. So similarly for this one, plus 12 is this way, so plus 12 is pointing downward, but it says minus 10, so I go counterclockwise 10 degrees that way. That's the graphical method. So now I can see that there's 50 degrees here, 10 degrees there, that's 60, there's a difference of 30 between them. And who leads who? That would be the other question. So the way you determine who leads in this method is you think about these vectors that they can rotate around in a clockwise fashion. And who hits 0 first? V2 does. So V2 leads because it hits the 0 axis right here first, so it's leading. It's all relative. So V2 leads V1 by 30 degrees. So lastly, I plotted this problem in MATLAB, and I hope you all are trying to use MATLAB because you'll need it at Manoa. So I set up my horizontal axis to be t going from 0 to 0.4 seconds because I knew the period was 0.2 seconds in increments of 0.001, and then I just did a plot function. So I have plot t. This is V1, plot t. This is V2 right here. So notice I have to say 2 pi f. Well, I put 2 pi f plus 50 degrees because your book kind of mixes it up. They made a 50-degree phase, but omega t is in radians. So I have to convert the 50 to radians. Same thing with the second function, V2, 12 times sine something. Omega t is in radians, but yet they give you a 10-degree phase difference, so you have to convert that phase difference not into degrees but into radians, and then I can plot V1 and V2. And so notice that V2 does indeed cross 0, positive going, before V1 does, so V2 leads V1. And by 30 degrees, if I convert it, is 0.5236 radians. And then I know that omega times t is radians, and it's 0.5236 radians, and I wanted to see what t that was, so I calculated it out. So V2 leads V1 by 0.0167 seconds as well. So it will cross 0 0.0167 seconds before V1 does. This leads us into the next section about phasors. So phasors, we're going to start analyzing circuits using a phasor representation, and that's going to make our life a whole lot simpler. So a moment ago we just did an example here, this example, and you can see that these equations right here are a time domain representation. So it's sine something, cosine something, plus phases of our signals that we're dealing with, our real signals that we're dealing with. But you can imagine if you had to start adding up a bunch of sines and cosines with different phases, that it can become a very complex problem. And I sort of leaded you into, this is the beginning of us having a phasor representation almost at this point. So anyway, this problem can become very complex when we have different phases to consider in our circuit. As a matter of fact, it can become what's called an intractable problem, which intractable means that it's unmanageable. It's so ugly that it's unmanageable, or maybe verging on unsolvable. So this man, Charles Steinmetz, came up with this method of using phasors, which we are going to learn about. And you will see that it greatly simplifies us doing an analysis of a circuit that's in a sinusoidal steady state with only one frequency present. And it's very important that we realize there's only one frequency present, and you'll see why. So before we go into using phasors to analyze a circuit, we need to be thoroughly familiar with complex numbers, and not just complex numbers, but moving between a rectangular representation of a complex number and a polar representation of a complex number. So let's go. So generically, a complex number z can be written as x plus jy. X is the real part, y is what we call the imaginary part, and j is the square root of -1. So remember, we as engineers are using j for square root of -1 instead of I, like somebody in math would use, because if we use I, we are at risk of confusing that with the current. So engineers use j so not to be confused with current I. So we have a rectangular form, which I just did, x plus jy, but we also have a polar form, which is in terms of r, which is a magnitude, and phi, which is an angular part, an angle. And then we have an exponential form, which you'll see how that ties in, where you still have r as a magnitude or an amplitude, and e to the j phi. So we'll see what e to the imaginary exponent means. So we have relationships between the polar and rectangular forms. You might have seen polar coordinate system in your calculus class, and then you're going between an xy coordinate system, a real rectangular or Cartesian coordinate system, and a polar system, both in real space, so both in real xy. In our circuits, we are going to be using a complex space, so we have a real axis and an imaginary axis. It's very similar to x and y, with the exception that real is real, and this is, like for a complex number, it's jy, so it's the imaginary axis. And so the relationship between r and x and y, where x, remember, x and y are the real and imaginary parts of a complex number z. So r is the square root of that, and the angle that's created by the real and imaginary portions is an inverse tangent function. So I have r right here, which you can actually say that, grab my pen back here. So it's actually written right here. This vector right here, z, and it is like a vector, it's actually going to be a phasor, but z equals x plus jy. So this is the x component, this is the imaginary part right here, it goes in the y direction, in the plus y direction. And the magnitude of that, which is very similar to how you do vectors, is the square root of x squared plus y squared, because this is a right triangle. It just happens to be in complex space. And this angle over here is the ratio of the opposite length of over the adjacent length. Notice there is no j right here. It's not inverse tangent of jy over x. It's inverse tangent of the lengths. So the length y and the length x. And so since we have this kind of a structure, you can say r cosine phi gives you x, r sine phi will give you the y length. So that's from your trigonometry, you should already know. So then we get the full complete relationship between the polar and rectangular forms, even though we're in complex space. So you can write it all these different ways. We need to be able to go between the two. So it turns out that if you are going to have complex representations, whether they are in rectangular or polar form, it turns out that addition and subtraction are very easy to do when you're in rectangular form. So I have two complex numbers, z1 and z2, represented by, as you can see how they're represented. And so if you want to do addition, you have to add up the real parts separate from adding up the imaginary parts. So and if you want to do subtraction, it's still you subtract the real parts plus then the imaginary part is a subtraction of the imaginary part. So watch that on subtraction. You did not change the sign here between the real and the imaginary parts. Multiplication is easier done in the polar coordinate system. So if I have two complex numbers and I've expressed them in polar form, then you can multiply their magnitudes and you can add their phases. Division, you divide their magnitudes and you subtract their phases. If I want to find the reciprocal of a complex number, here is just a complex number. Reciprocal of 1 over z is in polar coordinates is the easiest. There is a way to do it in rectangular coordinates as well. It involves finding the magnitude and then inverting the magnitude and then doing an inverse tangent to find the phase. So, but if it's easiest to do in already in the polar coordinates, so it would be, as you can see here. Now keep in mind, as a consequence of that, if you are going to do a reciprocal of something that's purely along the imaginary axis, so 1 over j, what's the magnitude of j? The magnitude of j is 1, but when you want to reciprocal it, it really means that you're going the opposite direction. That's the kind of the best way that I think of it. So let me show you what I mean. So I'm in complex space right here. Here's my complex space. So here's real, and here's imaginary, the imaginary axis. So this is 1 in the j direction. This is minus j in the opposite direction. And if you're doing a reciprocal 1 over something that's this way, you have to invert it and it goes the opposite direction. But that's how I think of it. Minus j is this direction, plus j is that direction. Square root, so if you want to square root something, also easier done in polar coordinate system. So you square root the magnitude and then it's the phase divided by 2. That's the angle. Oh, and this nomenclature means angle. Maybe I probably forgot to say that. That means the angle. So you have a magnitude and an angle. And then one thing we are going to need is a complex conjugate of a complex number. So if I have this complex number z, which is x plus jy, the complex conjugate, doesn't matter which coordinate system you're in, you change the sign of the imaginary part. Or you change the sign of the angle if you're in polar coordinate system. And then if you're in the exponential form, you will change the sign of the angle in the exponent up here. So that will give you the complex conjugate. So a complex conjugate of something is, drawing my picture out here in a minute, draw my picture. If I have some r right here at an angle phi, the complex conjugate of that is down here because it's now at an angle minus phi. And the magnitude stays the same. So this idea of a phasor is actually rooted in Euler's identity. And Euler's identity states that e to the, with the complex exponent, e to the j phi would be cosine phi plus j sine phi, or e to the minus phi is cosine phi minus j sine phi. That's Euler's identity. From this, that we can get that the real part is the cosine phi and the imaginary part is the sine phi. And a lot of times that we will write that cosine phi equals, and that means real part of e to the j phi, and sine phi is the imaginary part of e to the j phi. And the reason we do this, and you'll see why, is that in the future, that a lot of times these problems that would be very difficult to do in the time domain, we do it in the phasor domain, and we make everything into an exponential form sometimes. And then the exponential form is not the final answer. Exponential form is a tool for us. The final answer is that there is a real signal involved and you have to take the real part of it. This is especially true in electromagnetics. You'll see that when you get to that course. So, for example, we have a voltage as a function of time, and like earlier in this lecture, it's a Vmax cosine omega t plus a phase phi, and that's really the real part of this thing in a complex or an exponential notation right here. So it's really the real part of that. Going back, just to refresh for a moment. So I had my three forms. This is called the exponential form. But our real sinusoidal steady state solution will be the real part of an answer that's in an exponential form. Examples will help, I'm sure. So this real signal that we have, Vmax cosine omega t plus a phase difference, is really the real part of something that's in an exponential form. And notice I can take the e to the j phi part out separately by rules of exponent addition in the exponents. It can also be written like this, where the e to the j omega t is a separate exponential than the e to the j phi. And that's going to become what makes our phasor notation work. So taking that statement from the previous slide, here it is again. V of t equals the real part of this thing that's in exponential notation. I can rewrite it explicitly that V of t is the real part, and then what I've done here, you can see it. What I've done here is taken this part right here and called it something like a vector, but it's not really a vector, it's a phasor. So that part becomes a phasor. Here it's explicitly defined. This V is the phasor representation, and it's got a magnitude and a phase associated with it in our exponential notation, so we can write it as a magnitude and a phase. So that's the V part. And the actual final solution, the voltage that we're looking for as a function of time, is the real part of this entire expression. So this V part is what's going to become the thing that we want to use. This is the phasor representation of the sinusoid V of t. And the sinusoid V of t, of course, is going to equal a Vmax cosine omega t plus a phase difference. So we're going to do our problems with a phasor notation. It's going to be much easier than doing things with sines and cosines and omega t's and phases to keep track of, and we won't have to apply all those trig identities for sine a plus b, and it'll become much easier. So we call this portion, sometimes it's a little obscure, called a sinor. So it has a sort of a vector magnitude here is actually the phasor, and the e to the j omega t implied. So that equals V max e to the j omega t plus the sine, plus the phase, in complex space. So this sinor, this thing right here, is really regarded as a rotating phasor. And the picture down here below, it's really a useful construct for us. We see that the magnitude, the V peak, Vm right here, is the magnitude of this vector. And this vector is rotating around in a counterclockwise fashion at an angular rate of omega radians per second. So it's going around so many radians per second, which relates to the frequency. And then at a particular instant in time, we can be at a certain phase, which is shown by this phase right here. So we can project that. This is in complex space right now. And if we just take the real part of it, the real part of it is going to translate to something that looks like a cosine function. And then, so cosine of this vector that's rotating around gives you something. Oh, this is a mistake. This should say real right here. Real, and this should be imaginary in your textbook. Oops. So this is imaginary, this is real. So cosine of this will give you a real part. Actually, if we're flipped this way, it could be sine. Yes, it would be then. So sine would be the real part then, projected along the real axis. I guess that's what they're doing. It's a little bit atypical to do it that way. So they made the real axis going this way and the imaginary axis going this way. I think just to confuse you a little bit. But so if you say this vector this vector's magnitude, I want to project it. It's a projection, so it would be a cosine function, right? Or they have it doing as a sine. Okay, they have it as a sine function projected along the real axis. So this length right here gives you that value right there. And as this approaches this angle right here, it is a cosine. So this length is projected right here, Vm cosine something. And then when it gets, said it backwards. Forgive me, I just wasted a couple of minutes of your time. So you can project it when it comes around this way, for example. If you say sine of that, that's 0, and so sine of that has crossed 0 right here. Sine of it right here, sine of this angle is at this maximum right here. And so as it rotates around and you project it with, in this case, sine and the real axis being this way, which is a little bit not typical to do, you will trace out this sinusoid. So it's the real part is what's happening in the circuit. This imaginary space construct is good for us to keep in mind because it keeps, first we need to remember that we have a frequency happening in this circuit and that this voltage is got an angular rotation associated with it that causes its amplitude to be maxes and mins and zero crossings. So this is a plot of the real part of that, but you can extract the omega t part along the time axis, but a lot of times the term e to the j omega t is left out in the phasor representation, and we strictly work with this phasor vector part cap v. I think that will come clear in an example in a moment. So this was our time domain representation that we started with at the beginning of this lecture. Circuit problems can become intractable using this time domain representation. And then after we applied Euler's and considered complex space, we come up with this phasor domain representation. And it is a frequency domain representation, although the e to the j omega t is often left off. But you have to remember that there is something that's oscillating at a certain frequency omega in the circuit. The voltages and currents are oscillating at that frequency. And the magnitude of this voltage is going to depend on that oscillating frequency. which we'll see when we define our reactance coming up for our circuits. So, so this is just a picture kind of showing that this is a phase diagram, so it's a phasor diagram showing phasors. I have a phasor of voltage right here, and I have a phasor of current right here. And you consider that everything is rotating in this imaginary space at a frequency of omega radians per second. And the part that's confusing about this drawing, it has a leading direction and a lagging direction. But this is what you need to think about. You need to think about these two things rotating around together. The relationship between V and I, whatever this angle is between them, is staying constant. So as it rotates around, it's a question of which one crosses the real axis first. So if I look at this, if I start Vm right here along the real axis and Im down here, and then I start rotating, Vm crosses first, which would make Vm be leading Im. So V is voltage is leading current in this example. Or I is lagging behind V in this example. And omega is always going around clockwise. You can also say that V is a magnitude right here with a phase associated with it. So here it is, it's a magnitude and a phase associated with it. And I is a magnitude and a phase associated with it. So one of the things is that they said they showed here as being minus theta. So one of the things that we will keep track of when we go and start these circuit problems coming up is that we are, even though it's going around a full 360 degrees or 2 pi radians, we almost are always thinking about staying in these two quadrants right here. The vectors almost always are being drawn in these two quadrants, because it'll turn out that this means the circuit is more inductive over here and capacitive over here. When you get something that's over here in this quadrant, you almost always have to through our math translate it over in this quadrant so we can get the proper relationship between our phasors. Again, I think examples are going to help that. The point in this section of your textbook is to make sure that we can work with the complex numbers, and we will do a few examples. So, but here's a summary table of what I have somewhat just been saying. But I want to make the point here is that when we are expressing things as a sinusoidal function with an argument omega t plus a phase, we are expressing it explicitly in a time domain representation. We can take its magnitude, neglect or imply the omega t part, and keep track of the phase, and then we will get a phasor domain representation, which is actually a way of working in the frequency domain for us, but only in the case when we have a single frequency in the circuit and not more than one. So I told you about multiplication, division, addition, subtraction, reciprocals, and square roots. So it would not be complete without mentioning differentiating and integrating. So differentiating something in the time domain is equivalent to multiplication by j omega in the phasor domain. And integrating is equivalent to dividing by j omega in the phasor domain. And you can prove that using Euler's identity. So you have Euler's identity and you take the derivative and see what you get. So the differences between v of t, the time domain representation of our signal, and cap v, bold, like this, which is our phasor representation, needs to be emphasized. So I clipped this out of your book because I do really want to emphasize it. V of t is an instantaneous or time domain representation, which means I can put a value of t and get an instantaneous voltage. It may be at a max, it may be at a min in the cycle, it can be somewhere in the cycle. While v is a phasor or frequency domain representation. It is not instantaneous. It is a tool that's going to allow us to add up and compare different magnitudes and phases within a circuit. V of t is time dependent while v is not, and we often forget this, but our solution will always have an e to the j omega t component to it, which means that our solution, while it's expressed in terms of a phase and a magnitude, that instantaneous voltage still varies as a function of omega t. V of t is always real with no complex term, while v is generally complex. So even though we can write something in an exponential form, which has a complex portion of it, especially as when we apply Euler's formula, the final solution is always something real. So phasor analysis applies only when the frequency is constant, and it applies the manipulation of two sinusoidal signals only if they are of the same frequency. So then I'm at an hour on this YouTube. I don't like them to go further than that. So my next YouTube will have examples, and then we will learn about circuit elements and apply it to the circuit elements. But that'll be the next lecture.